Make sure you're doing your seating charts. So y'all know what next time I see you is. An exam? I remember this? Yeah. Just checking. Masks up, cover noses and mouths, please. Thank you. Okay, so what is on the exam next time I see you? Chapter 5, sections 5 and 6. What are covered in those two sections? Everybody remember? Condensation, hydrolysis, hydration, and remember all the different reactions? And you had reactions with the double bond, right? So hydrogenation and hydration, yeah. Okay, so go back, don't forget to study that. And then all of chapter 6 and all of chapter 7 is on the exam, right? Any questions about that? Okay, I made that video that y'all asked for. Remember the worksheet we did last week that we didn't get to the second page? I did the video for it. I sent you an email with it and I posted it in the chapter 6 material. Any questions on that? So your next homework is due tomorrow night for chapter 7. Okay, so we're going to finish chapter 7 today. And we are actually going to do our eye clicker a little bit later in the class. So make sure you have your eye clicker, but we're not going to start with that today. So make sure you've done your seating chart. And if you're looking for the video of reducing sugars, it's the same place where you find the activity itself in the chapter 6 material. Okay, so chapter 7. This is kind of where we left off, right? We're talking about hydrogen bonds, all the different kinds of intermolecular forces that occur between molecules. So one of the intermolecular forces that occurs between molecules occurs in molecules that have charges. Let me see if I can make this full screen. Right? Okay. So right, name 2 functional groups that contain ionic charges. Why is it important to know what functional groups carry ionic charges? Because they can participate in a different kind of intermolecular force. So if we skip down real quick, right? These are all of our intermolecular forces. What is the definition of an intermolecular force? Is it a bond? Well, the strongest one at the very bottom is an ionic bond. The very strongest one at the very bottom, this is an ionic bond. It's an attraction between a fully positive and a fully negatively charged particle, right? So like NaCl. What is NaCl? It's an ionic compound because the sodium carries a charge of +1. Chlorine carries a charge of -1. So an ionic interaction is one where you have a negatively charged particle and a positively charged particle. Do we have that? Yes. Okay. Go to the next one. Ion-Dipole. So this is an interaction between something that is charged and something that has a dipole. What is an example of this from the lecture? I have a feeling people aren't watching the lecture. What if I took a block of salt and I dropped it in a glass of water? What would happen? The salt would be dissolved by the water. Why? Because of ion-dipole interactions. What are ion-dipole interactions? An interaction between something that has an ion, so let's just say NaCl, we have two ions here, and something that has a dipole. Does water have a dipole? Yeah, absolutely. So how would that work? Water, H2O, right? If I were to draw H2O, there's part of that molecule that's positive and part of that molecule that is negative, right? Partially positive, partially negative. Remember that? So what would surround my sodium atom? Water, but water in a particular orientation. So my sodium's positive. So what part of the water is attracted to the positively charged sodium? The negatively charged portion, right? So it's really the oxygen, right? Because we have this dipole where this is partially negative. These are partially positive, right? So you would have water molecules that would surround that sodium ion and dissolve it. What about with the chlorine? What part of water would associate with chlorine? The negative, the chlorine is negative, so it would be the hydrogens that would associate with the chlorines because they're partially positive, partially negative, partially positive, right? So positive attracted to negative, negative attracted to positive. So that's an example of ion dipole. What's the next weaker type of interaction? Hydrogen bonding. What is the definition of hydrogen bonding? Remember, it's no what? No fun. It is a hydrogen attached to nitrogen, oxygen, or fluorine that interacts with another electronegative atom of nitrogen, oxygen, or fluorine, right? Yeah. So that's a type of, that's hydrogen bonding, but by definition, hydrogen bonding is a type of dipole-dipole interaction. Water can undergo dipole-dipole interaction, right? There's a dipole in water, so water can interact with water, absolutely. But it's a very strong interaction. So we call hydrogen bonding a type of dipole-dipole. It's the strongest type of dipole-dipole interactions. Okay, and then what is the very weakest one? London forces. What has London forces attractions? Everything. Everything has London forces. Or London, have you heard London dispersion? And forces, people abbreviate it LD, London dispersion forces, LDFs, right? London dispersion forces. It just means that your electron cloud moves. It gets dispersed. Okay, so everything has London dispersion forces, everything. Okay, so now, in order to identify if something is having an ion-dipole interaction or an ionic interaction, you have to look and see what kinds of functional groups have positive or negative charges. So looking at your functional groups, remembering your functional groups, what two do we have that contain ionic charges, not partial charges, but full charges? What are the two? I'll tell you, they're ones that hydrogens can come off and on. And that's what gives it the charge. Go look at your chart. Not a good sign. Okay, I'll give you a hint. What does a carboxylic acid look like? It's an R group attached to a carbon, double bonded to an oxygen. And what else does it have? It's a carboxylic acid. It has an OH. Does this have a charge? No, but what can happen? Remember, I was talking about hydrogens. What can happen? Does hydrogen come off or do we add it? Comes off. So what do we end up with? O minus, right? Because we lost the hydrogen. So this is now no longer a carboxylic acid. This is carboxylate. B-O-X-Y-L-A-T, carboxylate. So carboxylic acid is not ionic, but carboxylate is. And that's going to be really important later. That's one of them. What else? Protonated amines. Pure O. Protonated amines. What's an amine? An R group that's attached to a nitrogen. And then you can have primary, secondary, tertiary amines, right? So what does that mean? Primary, what if I said you had a primary amine? How many hydrogens would be attached to that nitrogen? Nope. That's talking about the R group. The primary tells me how many R groups are attached. So this is actually 3 and it's positively charged. A secondary amine would have how many R groups? 2. So then I'd have a nitrogen and then I'd have 1 less hydrogen and it would be positively charged. If I had a tertiary amine, I would have how many R groups? 3. I would have a nitrogen with 1 hydrogen and it would be protonated. It's a protonated amine. So if you go and look in your book and you look up amines, you will see that they have 1 less hydrogen than what we listed right here. It's protonated. So what does protonated mean? It has an extra proton, which is a what? A hydrogen. That hydrogen is positively charged. Okay. What makes the nitrogen? The hydrogen makes the nitrogen positively charged. Okay. All right, so let's go on and talk about all of these different forces. Okay, identify the strongest attractive force present in a pure substance shown. Which one is strongest? Is it London forces, dipole-dipole, hydrogen bonding, ion-dipole, or ionic attractions? So look at A. What do we have in A? What my suggestion is to look for functional groups. So what functional group do you see in A? An OH, a hydroxyl, right? So tell me about that hydroxyl. We call it an alcohol or a hydroxyl. What are the properties of oxygen bound to a hydrogen? I have an R group that's bound to a carbon with 2 hydrogens and an OH, right? That oxygen has 2 lone pairs on it, just like water does. So tell me what happens to that oxygen. Oxygen is partially, hydrogen is partially positive. What can happen with this? If I had another molecule, right? If I have a cup of this substance, I have lots of these molecules floating around in the cup. So if I had another molecule of this, what could happen? I could have my hydrogen that's attached to my oxygen, that's attached to my carbon that has 2 hydrogens and an R group. This hydrogen here is partially positive. This oxygen here is partially negative. So I could have an interaction between this partially positive hydrogen and this partially negative oxygen. What kind of an interaction is that? Take a guess. There's 5 there. Is it London forces? Yes or no? Technically, yes, London forces is present. Technically, all molecules have London forces. So technically, it is present. But we're asked to identify the strongest attractive force. Okay, next, dipole-dipole. Do we have 2 molecules that each have dipoles? Yes, we do. Now, is that dipole-dipole interaction a type of hydrogen bonding? Yes, it is. Do we have completely oppositely charged particles in our mix? No, we have partial positive and partial negative. That gives me a dipole, but I do not have an ion. So I cannot have ion-dipole, I cannot have ionic. Y'all see that? So what is the strongest type of interaction that happens in A? Hydrogen bonding. Yes? Okay, let's do the next one. I'm gonna erase my work on the side here, so I have room to do each problem. Okay. KCl. If all I have is KCl, what do I actually have? K is in group 1, that's a +1. Cl is a -1. So what kind of forces do I have? Do I have London forces? Yes, I do. Do I have dipole-dipole interactions? I don't see a dipole there. Do you see a dipole there? Dipole tells you partial charges. Do you see dipole? No. So can there be hydrogen bonding? Hydrogen bonding is a type of dipole-dipole interaction. No. Ion-dipole. We don't have a dipole, so we can't have ion-dipole. Do we have ionic? Absolutely yes, because we have a fully positive and a fully negatively charged particle. So yes, we have ionic. Y'all seeing how I'm going through each of them? Okay, so let's look at the next one. Okay, the next one is CH2Cl2. So I have a carbon atom in the middle. It has 2 hydrogens and it has 2 chlorines. What can we say about this molecule? Let me ask you this, London dispersion forces, yes or no? Yes. Dipole-dipole interactions. The question is, do we have a dipole? How do you know if you have a dipole or not? Can you go to your best friend and go look at electronegativity values? Yes, so go to your best friend. Is there an electronegativity value between chlorine and carbon? I'm serious, go to your best friend. Your best friend should be out and ready to go and ready to help you. Do we have an electronegativity value difference between carbon and chlorine? Yes, we do. Yes, we do. Who's more electronegative? Chlorine is more electronegative. So I'm going to put my arrow to point at the negative. I'm pointing at the negative, right? Is there an electronegativity value difference between carbon and hydrogen? Technically, yes, but it's so small that we just pretend it doesn't exist, right? Remember that? So if I were to draw an overall dipole moment, do I have a dipole moment in this molecule? Yes, and it kind of goes like that. So do we have a dipole? Yes. So this is a polar molecule. That means that we have a dipole. It has a dipole. If it has a dipole, guess what kind of interaction we can have? Dipole-dipole. Okay, so we said yes to dipole-dipole. Do we have hydrogen bonding? No, we don't have hydrogen bound to an electronegative atom, so we can't have hydrogen bonding. Do we have ion-dipole interactions? Do we have any ions? I don't see anything fully negative or fully positive. Like a +1, a -1, I don't see that. So I don't have an ion. So can I have ionic interactions? No. So what is the strongest interaction that I have? Dipole-dipole. So that's what I wrote down here. Dipole-dipole. Good. Okay. The last one. The last one. What do we have? What is that? Carbonyl, right? Carbon double bound to an oxygen. So that oxygen has 2 lone pairs on it, right? Do we have an electronegativity difference between oxygen and carbon? Look on your best friend. Yes, we do have an electronegativity difference. So what are we going to do? What kind of a dipole is happening in this molecule, right? We have one bond that's polar. That one bond points to the oxygen because it's partially negative. So the carbon's partially positive. So what's my overall dipole moment? Looks like this. So do I have London forces? Let me erase this as last time. Do we have London forces? Yes, we do. Everything has London forces, everything. Do we have dipole-dipole interactions? Yes, we have a dipole, absolutely. Do we have hydrogen bonding? Do you have a hydrogen bound to no fun? No. Do we have ion-dipole interactions? No, because we have no ion. Do we have ionic interactions? No, because we don't have 2 ions. So what's our strongest for D? Dipole-dipole. Okay. Now I'm not going to give you this on the exam. So like maybe this is one of those things that when you get to the exam, you write down for yourself, like this. What are the attractive forces? And I'm going to list them from weakest to strongest. I would write that down. When I start it, you should probably jot that down, something. Okay. All right. Now, we have to not only be able to recognize what kind of interactions can happen, but we have to see where those interactions can actually happen. So we have this molecule CH2O, and we're going to put some of it in water. And what I want to know is how many hydrogen bonds can this molecule make with water? So if I were to draw this molecule, what would it look like? Be a carbon in the middle, right? Do your Lewis dot structure really quick. I'm not going to do it for you. You do it. Draw the Lewis structure of CH2O. You should be drawing a Lewis structure right now. So you should have ended up with something that sort of looks like this. Did I get that? Close? Maybe in different 3 dimensions, but basically the same thing. Okay, now it is in solution with water. Do I have polarity in this molecule? Is this a polar substance? Absolutely it is. What is partially negative in this scenario? Oxygen's partially negative, carbon's partially positive. So if I were to draw a dipole moment, it would look like this, right? Okay, so let's draw water. If I want to draw water, I want to draw it in the right orientation. So if I have a very electronegative oxygen, what part of water is that going to want to interact with? The positive part of water, right? The opposite. So what's positive in water? Hydrogen. So I'm going to put hydrogen, oxygen, hydrogen. Let's supposed to be an oxygen. Okay, so the oxygen over here is partially negative. This is partial positive, partial positive. So we can create an interaction between the partially positive oxygen of our CH2O and our partially positive hydrogen of water. So that's one hydrogen bond that could occur. Where else can it occur? Now, here's the thing to remember. Everywhere where you have a lone pair, you can accept a hydrogen bond. So how many lone pairs are on that oxygen? 2. So I can make another hydrogen bond with another water molecule, right? So this oxygen functions as an acceptor. Here's another acceptor. And then this hydrogen is a donor. This hydrogen is a donor. Can my hydrogens that are over here on the carbon, can these be donors? I see people shaking your head, and that's correct. Why can't these be donors? Are they bonded to an electronegative element? No, they're bonded to carbon. So they're pretty happy. They're pretty close in electronegativities. So this cannot be a donor. So how many hydrogen bonds can CH2O make with water? Only 2. Okay. So why are all these intermolecular forces so important? And why do you have to know how many you can make? Because when you figure that out, you can tell about the properties of those substances. So I can look at the intermolecular forces, and I can tell whoever's got the strongest intermolecular forces, they are going to have the highest boiling point, the highest melting point, and the lowest vapor pressure. So this is boiling point, melting point, and this is vapor pressure. So let's talk about these 3 things real quick. What is boiling point by definition? What's the phase change that happens for boiling point? If I boil water, what happens? It converts from a liquid to a gas. So boiling point is converting liquid to a gas. So the stronger the interaction, the higher the temperature it takes to turn that liquid into a vapor. Yeah? Okay. What is melting point? Solid to a liquid, right? If you're going to melt water, you have an ice cube and you melt it into liquid water, right? So the stronger the interaction, the higher the temperature it takes to melt something. We okay on that? All right, now the last one's a little tricky. Do you see how it's opposite boiling point and melting point? Okay, so you got to pretend that I have like a bottle of water, right? If I heat that bottle of water, what's eventually going to happen? And it doesn't melt. Let's say it doesn't melt. That liquid inside the bottle of water is going to get converted into what? A gas, right? And eventually that thing will explode, right? So you have to think about, what is vapor pressure? Well, when liquids turn into gases in a closed container, those gases exert a force on the liquid and on the sides of the container. So the more stuff that turns into a gas, the higher the pressure. So this is why it's opposite. If you have a high boiling point, right, that means it takes a lot to get it to turn into a gas. We're going to conversely have a very low vapor pressure because not a lot of it is in the gaseous state. So the stronger the interaction, or the more of the same interaction you have, The higher your boiling point, the higher your melting point, the lower your vapor pressure. That is not on your best friend. So what should you do with this information? Write it down. This is one of those things that you want to write down when you get your exam. I know people who like get their exam, they don't even look at it. They flip it over and they just write for like 5 minutes. You know, set yourself a timer or give yourself a certain amount of time. You can't set yourself a timer during the exam, but you know what I mean? Give yourself just a few minutes, write down the important stuff, practice doing that at home. Then you don't get yourself confused in the exam. Okay. All right. So predict which pure substance, this means that we're not in water. Predict which pure substance will have a lower melting point, baking soda or phenol, and explain your answer. So let's talk about this one first. What kind of a substance is this? NaHCO3. If I were to tell you to name that molecule, how would you name it? What is Na? Sodium. Maybe you want to go see your best friend. Where would you go on your best friend to finish naming this molecule? Polyatomic ion table. Go look for that. What do you see? Either sodium bicarbonate or sodium hydrogen carbonate. What do they say for y'all? Either way works, doesn't matter. So hydrogen carbonate or, so they give you both. So we'll say sodium hydrogen carbonate. But the point is that this is a polyatomic ion. And this is a what? Did you get it off the table here? No, where'd you get it? From the periodic table. What kind of an element is it? Is it a metal, a non-metal, a metalloid? What is it? It's a metal. So what do we call a compound that's a metal and a polyatomic ion? We call it ionic. So what is the strongest type of force that's present for this pure substance? It's ionic. It's absolutely ionic. So it's an ionic compound, and it has ionic intermolecular forces. Call them IMFs, intermolecular forces. Okay. Tell me about phenol. C6H5OH. Is this an ionic compound? No, it is not. It is a covalent compound. How did I know it was covalent? They're all what? They're all nonmetals. But I see something in there. Do you see something in there? I see a hydroxyl. So this is covalent with a hydroxyl or an alcohol, whichever way you want to say it. So if you have a hydroxyl or an alcohol, what kind of intermolecular forces can you have? Do you have a hydrogen bound to an electronegative element? Absolutely. So what is the strongest force that occurs if you have a hydroxyl? Hydrogen bonding. So which one is stronger? Which one has the stronger interaction? Ionic. This is stronger. This is stronger intermolecular force. This is weaker intermolecular force. Okay, but that's not what the question asks. It says predict which pure substance will have the lower melting point. So come up here. Melting point, right? The stronger the interaction, the higher the melting point. I'm looking for high melting point or low melting point? Low. So if I'm looking for a low melting point, I need a weak interaction. So which one's the weaker? Is my phenol. So my phenol, because phenol has the weaker intermolecular force, it has a lower melting point. Boy, we put a lot of things together with that, didn't we? Yep, that's why this class builds. It builds and builds and builds and builds. So if you miss something, you're going to find out now. So if you struggle with something, come ask me for help. Okay. Same thing. Let's do some more molecules like that. All right. Rank the following compounds in order of increasing boiling point, lowest to highest, and explain your ranking. Okay, I'm going to write my little thing on the side, right? If I have stronger or more intermolecular forces, what do I know? I have a high what? High boiling point, I have a high melting point, and I have a tricky, low vapor pressure. Actually, the P is supposed to be capital because it's not point, it's really pressure. Okay, so let's talk about each of these three compounds. That first compound, what functional group is in there? Do you remember when I said you had to learn your functional groups and they were really important? What functional group is there? It looks like this, ROR. That's an ether. That's an ether. So really we have an oxygen with how many lone pairs because it has two bonds with it. Remember, an oxygen with two bonds has two lone pairs. So tell me what can happen with this ether. What kind of interaction can happen? Do you see anything that is a full positive or a full negative? So we can't have ionic, we can't have ion dipole. Do we have a hydrogen bound to an electronegative element? No, all our hydrogens are bound to carbons. Do we have a polar molecule? Yes, we do. Yes, we do. We have some polar bonds going on. So what kind of interaction can happen? Dipole, dipole. Okay. All right, now, the second one, what do you see? What functional group? Alcohol, LCOHOL. Oh my gosh. Or a hydroxyl, however you want to think about that. So what is the strongest? This is one thing you should just like automatically know. What is the strongest type of interaction that can happen with a hydroxyl? Hydrogen bonding. Can you tell me how many hydrogen bonds can form in this molecule? Remember, you have 1, 2, 3, 4 lone electrons, so you have 2 lone pairs. How many hydrogen bonds can you make? You have 2 acceptor sites and you have 1 donor. The hydrogen is the donor, the lone pairs are acceptors. So you can make 3 hydrogen bonds. Okay, how about the last one? What is that? That's a simple alkane, right? All carbon-carbon single bonds. So what's up with that molecule? Is it polar? It's carbons and hydrogens. We said there's no real electronegativity difference between them. So is it polar? No, this is a non-polar molecule. This is non-polar. So anything, if all it has is carbons and hydrogens, it's non-polar. So I don't have anything polar. I don't have anything charged. What is the strongest type of intermolecular force that I have? I have London dispersion forces. So rank the following compounds in order of increasing boiling point. Before I do that, I'm going to write weak, stronger, and strongest under each of them. So which one is the weakest? My London dispersion forces. So this is weakest. Which one's the strongest? The strongest is the alcohol. Okay. And then in the middle, right? I'll say middle is my ether. Y'all with me so far? Okay, so now I need to rank the compounds in order of increasing boiling point. So I'm going to start with the lowest boiling point. What is going to have the lowest boiling point? The one with the weakest or the one with the strongest intermolecular force? The one with the weakest. So this is the lowest boiling point. Which one has the highest boiling point? The alcohol has the highest. And then my ether. So this is in the middle. So if I'm going to rank them from lowest, from increasing boiling point, so the lowest is 1, 2, 3. Yeah? Okay. All right. So this next one, we're going to do that. We're going to use the same little thing. So remind me if you have the strongest or the most intermolecular forces, what do you have? The highest boiling point, the highest, and the lowest vapor pressure. Okay. So we have two common inhaled anesthetics, desflurane and halothane. They both have boiling points of 23.5 degrees Celsius and 50.2 degrees Celsius, respectively. Which one is predicted to have a higher vapor pressure at a given temperature? So we have our two. And I'm going to say this one has 23.5 degrees Celsius. This one is 50.2 degrees Celsius. This is for boiling point. Okay, which one has the highest boiling point? Desflurane or halothane? Halothane. This is the highest boiling point. So I want to know which one is predicted to have a higher vapor pressure. So if I have a high boiling point, that means I have a low vapor pressure. So highest boiling point would mean lowest vapor pressure. This one has the lowest boiling point. So we'll have the highest vapor pressure. So which one has the higher vapor pressure at a given temperature? Desflurane. Yeah. How nice is it to have this written? Yeah. Don't forget to write it. Okay. Don't forget to write it. Okay. Now, when we talk about whether things have attraction to one another or not, it also tells us about solubility. So have you ever wondered why when you put salt into water, it dissolves? It's because of the full charges on the sodium chloride and the partial charges on the water. So the more of those dipoles and full ion charges there are, the more they're going to be easily dissolved in water, right? How about oils? Do you think they have a lot of polarity to them? Are they soluble in water? No. So have you heard the thing like dissolves like? Have you heard that before? Do you know what it means? If your solvent is water, what kind of a molecule is water? It's polar. So polar things dissolve in polar water. Now, if I had something non-polar, right, is it going to mix with water? No. But if I had two non-polar things and I put them together, would they mix? Yes. So have you seen like salad dressing, right? If you have oil and vinegar, vinegar is mostly water, right? If you put your salad dressing on the counter, what happens? Separates, right? And you have to shake it up to get them to mix. But if you put it back down, they separate. Same thing if you're boiling water and you're doing pasta and you pour a little oil in the water, what happens? You end up with those little circles of oil, right? Because they're not mixing, because they don't have the same polarity, right? So cool. Okay. So based on their polarity and attractive forces, because polarity tells us what kind of attractive forces are going to be present. Predict whether the following compounds are soluble, insoluble, or form a micelle in water. NaCl. This is an ionic compound. What kind of attractive forces is it going to have? With water. So NaCl plus water will have what kind of forces? Come on, y'all. Remember the little flow chart from earlier? Which one? Will you have London dispersion? Yes, of course. Everything's yes. Will you have dipole-dipole? No, not between NaCl and water. Between water molecules, yes, but not between NaCl and water. Will you have ion-dipole interaction? Between NaCl and water? Yes, NaCl is a positive and a negative, and water is polar. So you're going to have ion-dipole intermolecular forces. Okay, so is this soluble, insoluble, or will it form a micelle? Use your common sense. If I put salt in water, will it dissolve? Yes, it's soluble. I actually posted in chapter 7 at the end of all the lecture videos, I posted a little animation of how the dissolving process actually works with NaCl and water. Because sometimes you just need to see it. Okay, so you can use a little common sense to answer these. Sodium stearate, and we'll talk about what this 18 to 0 means in just a minute. A fatty acid salt. What's a fatty acid? Remember I had you draw fatty acids? Do you remember this? Yeah. So a fatty acid, it has an acid, so it has a carboxylic acid, right? I don't know why I put it far away. And then it's bound to carbons, right? And this is telling you how many carbons are there. There are 18 carbons there, and there are no double bonds. So it's all single bonds, and I'm not drawing all 18, but this is basically what a fatty acid looks like, right? So what's a fatty acid salt? In a fatty acid salt, you've lost the hydrogen, and now you have a carboxylate, which is negative, and you bond it to a positively charged metal. So do you see how you have a positive and a negative? What are salt compounds? ionic compounds that have a positive and a negative. So this is what kind of interaction? Right? This is an ionic interaction here, right? Between these two. But what I want to know is this plus water, what do we have going on? We have an ion-dipole intermolecular force. And you could have just looked at the word salt and known that, because water has a dipole and salts are charged. Okay, isopropyl alcohol. What do we have in isopropyl alcohol? We have an alcohol. So an alcohol or a hydroxyl plus water, these are both what? They both have dipoles, but is that the strongest interaction that's present? No. What kind of interactions can alcohols and water do? Hydrogen bonding. Okay, so, and we didn't even answer. So in C, if we have hydrogen bonding occurring between water and alcohol, is it soluble or insoluble? What's that? Have you gone to the store and have you purchased 70% alcohol? Like rubbing alcohol, right? So if it's 70% rubbing alcohol, what in the heck is the other 30%? It's water. When you get it, do you see layers? Nope. So what is it? It's soluble. Okay, and then the fatty acid salt. Is the fatty acid salt soluble or insoluble? I forgot to do that. Now be careful, it's soluble here. But what about over here? It's not. So it's going to interact here on the polar portion, the ionic polar area. You're going to have that ionic dipole interaction. But here, you're not. This is a non-polar portion of the molecule. So this is how soaps work. Soaps are fatty acid salts. So we have portions that will interact with the water, and then we have non-polar portions that are long fatty acid tails. So what happens is in water, they make what's called a micelle. Have you seen micellar water? Guess what you got in there? Some fats, some oils. It's not micellar water. Water doesn't form a micelle. That's crap. You put something else in there that forms a micelle. And what happens is, this is how your detergent works in your washing machine, the hand soap at your sink, is that dirt is nonpolar. So the nonpolar tails will interact with the dirt and will surround it. And then those polar head groups over here, these polar head groups will interact with the water. And so they'll surround these little dirt particles. You're not dissolving anything. You're just sending it down the drain. You're just pulling the dirt off of your clothes, sending it down the drain. You're pulling the dirt off of your hands and sending it down the drain. You didn't actually get rid of it. You know what I mean? Isn't that cool? So many things you never knew you wanted to know. Okay. All right. Predict which of the following compounds is likely to be more soluble in water. So we're not saying are they soluble, we're asking more soluble. So look at A, look at the first compound. What kind of functional group do you see? What is that? Alcohol. If I have an alcohol, what can I do? Hydrogen bonds. Is it very soluble in water? Yeah, super soluble. Super soluble. How about CH3, CH2? Any functional groups? This is really an alkane. Tell me about alkanes. Are they polar? No, these are non-polar substances. Are they soluble in water? Or in water? No, they're not. So this is insoluble. So which compound is likely to be more soluble? First or second? First one. Okay. CH3NH2 or H2S. Maybe we might have to draw this one. Do you want to draw this one? Some people say no. Can you do it without drawing? First one or second one? Okay, let's draw it. If I have a nitrogen, this nitrogen has 2 hydrogens attached and it has a methyl group, right? What's on that nitrogen? If you drew this Lewis structure, what's on that nitrogen? A lone pair. Do I have a hydrogen bound to an electronegative element included in no fun? Yes, nitrogen. So I can have hydrogen bonding. Okay. Now, H2S, I have S, I have 2 hydrogens. If I drew this in Lewis dot structure, how many lone pairs? 2 lone pairs. So kind of like water, right? See how sulfur is in the same column as water? So H2O is going to have the same shape as SH2 or H2S, however you want to say that, right? Okay, so what kind of interaction can this be? This is dipole-dipole. Do we have hydrogen bonding? No. Do we have hydrogen bonded to no fun? No, so we can't have hydrogen bonding with water. Okay, so which one? CH3NH2 or H2S? More likely to be soluble. The first one. Hydrogen bonding has stronger interactions with water than dipole-dipole. They'll both be soluble, but which is more soluble? Hydrogen bonding, because it's a stronger intermolecular force. Okay. Now we're going to change gears a little bit and we're going to talk about fatty acids. So fatty acids can be combined inside of our body to make functional things. One example of something is a triglyceride. So what do you think is going to be in a triglyceride? What does tri refer to? 3. What does glyceride refer to? Glycerol. Y-C-E-R-O-L. Glycerol. So you have 3 fatty acids hooked to a glycerol molecule. But the question is, what's a glycerol, right? We've talked about fatty acids, but we haven't really talked about glycerol. So glycerol is 3 carbons in a chain. And each carbon has a hydroxyl group. Oh, I don't know why I did that. Each carbon has a hydroxyl group. Now, complete each carbon's octet with hydrogens. What does the top carbon need? 2. So I'm going to just do that, H2. What does the second carbon need? 1. What does the third carbon need? 2. This is glycerol. Okay. I'm going to need room, so I'm going to erase this stuff. So now, what is a fatty acid? Fatty acid is an OH, right? It's attached to a carbonyl carbon, and then we have a fatty acid tail, right? A nonpolar tail. Yes, remember this? Okay, how many of these do I have? If it's a triglyceride, I have 3. I got lazy and they started to look like waves. Okay. So now, what happens to turn a glycerol and 3 fatty acids into a triglyceride? I have to hook these 4 things together. How am I going to hook these 4 things together? What I can do is I can pull a hydrogen and a hydroxyl, and what can I make? I can make water, right? I can pull those out and I can make water. So what would happen if I did that? I'm going to erase them, and maybe will it let me pull it over? What did I do? What kind of reaction was that? I produced water. Condensation reaction. Do the same thing with the others. Get rid of 1 hydrogen and then a hydroxyl, and then move it. Right? Now, could I get rid of this hydrogen right here and this hydroxyl? Sure, absolutely. It doesn't make a difference, right? Let's do that. We're going to get rid of that hydroxyl and just that hydrogen. Then I'm going to take all this and move it over. I just made a triglyceride. Isn't that awesome? Don't you feel accomplished? Right? So what component molecules make up a triglyceride? We have, 3 fatty acids and 1 glycerol. And this happens in a condensation reaction. Okay, so now, not all fats are made the same, right? Do oils have fatty acids in them? Yes. Do fats have fatty acids in them? Yes, they do. So what's the difference between the olive oil sitting next to your stove and the butter? If I left them both out, tell me what state of matter they're in. Olive oil is a liquid. Butter is a solid. What in the world? Why is that? Butter is packed tight together like pages of a book. I mean, it's stuck together. It's stuck together due to London dispersion forces. So they have fatty acid tails. We're gonna do this on the side. Butter. And we're going to say olive oil, right? Both butter and olive oil are fats that have that carbon backbone, and then they have those tails, right? Butter is all unsaturated, which means what? What does unsaturated mean? Oh, I'm sorry. Butter is all saturated. Butter is all saturated. What does saturated mean? Covered in what? Hydrogens. So do we have any carbon-carbon double bonds? None. So this is no carbon-carbon double bonds. None. They don't exist in butter. You've heard of this, saturated fats and unsaturated fats, right? We've talked about this. So because those fatty acid tails are straight, they can pack together like pages of a book. The more they pack together, the more London dispersion forces they have. That holds it together. So at a particular temperature, butter, like room temperature, butter is a solid. The opposite is true for olive oil. Olive oil is the same thing, except we're going to get some carbon-carbon double bonds in there, right? And those carbon-carbon double bonds are going to prevent perfect packing. So it's like sticking something into your book, right? And it makes this big old hump in it, big old lump, right? It can't pack together as tightly. So we have the olive oil as an example of an unsaturated fatty acid. So we have carbon-carbon double bonds. These are typically cis, right? Remember we said that all naturally occurring things have cis carbon-carbon double bonds. The trans fats are the ones that we make in industry. So we have less London dispersion forces because of those carbon-carbon double bonds. They just can't pack together as tightly. Okay, so let's look at two oils, olive oil and soybean oil. Are they both liquids at room temperature? Yes, they are. They are. But they do have different melting points. They melt, one at -6 degrees Celsius and the other at -16 degrees Celsius, right? And room temperature in Celsius is about 25 degrees. So at 25 degrees are both liquids, but they have different melting points. So explain their difference in melting points. Well, tell me what has to be true. Talk about carbon-carbon double bonds. Which one do you think has more carbon-carbon double bonds? Let's not even pick which one. Let's say blank has more carbon-carbon double bonds. What does that tell you about the molecule? The more carbon-carbon double bonds, do you have more London dispersion or less? You have less London, I'm just going to do LDFs. Whoa. London dispersion forces. So if I have less London dispersion forces, tell me about my melting point. Oh my gosh, that thing you wrote down just a minute ago is really important. Tell me about melting point. Higher or lower melting point? Has a lower melting point. So which one has a lower melting point? Olive oil has -6, soybean oil has -16. Which one's lower? -16. So -16 is soybean oil. So the more carbon-carbon double bonds you have, the less you are able to pack those fatty acid tails in together. And therefore, you're going to have less interactions. The fewer interactions you have, the lower your melting point is going to be. And we already knew that, right? So we're just adding a little bit to that. Okay. So a lot of times when you look at fatty acids, you're going to see a name, and then you remember we saw those numbers in brackets, right? So what does the first number tell you? How many carbons? The second number tells you how many carbon-carbon double bonds you have. And then after that, you've heard this omega-3, omega-7, omega-9 fatty acids, right? On little like butter substitute things, yeah? So what that's telling you is this is the carbon, the first carbon that participates in the double-double bond, in the carbon-carbon double bond, excuse me. So the only thing with numbering is that you always find your carbonyl carbon and start numbering at the carbon that's farthest away. So then we go 1, 2, 3, 4, 5, 6, 7. An omega-7 would have a carbon-carbon double bond that starts between 7 and 8. But it's a 16-to-1, which means it has 16 carbons, and only one of those bonds is a double bond. Okay, so, right, one of the main triglycerides in palm oil is tripalmitin. It contains 3 fatty acids with carbon designations of 16-0. Do we expect this molecule to be a solid or a liquid at room temperature? So what do we do? What does this 16 tell you? We have 16 carbons. How many carbon-carbon double bonds? we have no carbon-carbon double bonds. So let's go, let's start. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16. Okay, so this 16 is going to be my carbon that's participating in the carbonyl. And then I'm also going to be bound to an alcohol. But this is a triglyceride. So instead of being bound to an alcohol, I'm bound to the glycerol, right? So you just take off the hydrogen and you bind it to a carbon, right? Ooh, let me extend the page. So I'm going to take, I wonder if I can copy that. Copy, paste. Okay, well, at least we got the tail, right? Okay, so we do the same thing for 3 because it's a triglyceride. And then we're going to come down, make an oxygen bound to a carbon, come down, oxygen bound to a carbon, link your carbons, give this carbon how many hydrogens? 2, this one, 1, this one, 2. It's easy because you didn't have to go in and build a double bond, right? Good. Remember, if you get that number here, then you're going to have to, if you get a 1, then it's going to be omega 3. And then that carbon-carbon double bond would be 1, 2, 3 between 3 and 4, right? So just make sure that you can do that. All right, very end. The very end is all about attractive forces in the cell membrane. So we all know what a lipid bilayer looks like, right? Where our polar head groups are all facing the water's out here, and those fatty acid tails are facing inwards to each other because they're nonpolar and they don't like the water at all. So they kind of hang out with one another, where those polar head groups are happy to hang out with water because water is polar and like dissolves like. So both of these are polar, so they like to hang out with each other, right? So draw a possible hydrogen bond between a molecule of cholesterol, oh gosh, and a molecule of water. What does cholesterol look like? Do you have to be able to draw cholesterol? No, but you have to be able to kind of recognize what it looks like. You don't have to be able to draw cholesterol. That'd be kind of mean of me, right? So I'm going to draw cholesterol for you. And if this were an exam, I would give you this. So that's a double bond. Then you have another one. It's always kind of fun to draw these. And up this way. And then you have like a little house, right? And then you come up and you have this, all cholesterol have these cyclic groups, right? Do you see all the little, you know, we drew them in sugars all the time, right? These cyclic groups. And then they have these non-polar tail groups that you can have all kinds of carbons going on. Depends on which cholesterol you have, what other stuff you have attached to all that. But basically you have cyclic groups, you have non-polar tails, and then on one end you have a hydroxyl. So out of all this stuff, what can participate in interactions with water? What do we see? What functional group? Hydroxyl. So what can participate? What do we do? All right, we're going to draw water, right? I know that this hydrogen can participate with what? With the oxygen in water, right? What else could happen? I could have this lone pair interact with a hydrogen, right? And I could have this lone pair down here participate with water. So what can happen? Hydrogen bonds. Hydrogen bonds can happen, right? It's just a hydroxyl. Like when people see this, they look at a cholesterol molecule and they're like, oh my God, this big old thing, what's going on? But you just have to focus in on the functional groups. The functional groups are going to tell you what interactions can happen. Okay. All right. So we got a few minutes. Take out your clickers. We're going to see how many clicker points we can get today. All right. These should be some easy ones. Y'all ready? A few minutes. See if we can boost up your clicker scores. Get your best friend out. You can leave your notes out. Y'all ready? Remember, exam next time. Here we go. All right, which relationship is inverse? When one increases, the other decreases. Remember, either use your peas and vegetables on the table or use Pivnert. Either one. Okay, 10 seconds. Make sure you click in, don't leave it blank. All right, turn and talk and click in again. It shouldn't matter if you're using the handheld eye clicker. You can't use them both at the same time. So you have to not use your computer and use your handheld.
I know, I don't answer on my computer. I just have it like popped up or whatever.
That's probably what's going on. But I think it doesn't like that you tried both at the same time.
That's what I do every class here.
It's not supposed to. Not supposed to. Okay. So we said 45 seconds. I'll give you a minute because we were chatting. So make sure you've clicked in again. Okay. So what did y'all say? Good, very good. So D is correct. D is correct. How did you do that? I do Pivnert, right? And which two variables listed are on the same side of the equation? Because if they're on the same side of the equation, they have to be inverse. Because left side always has to equal to the right side. So if pressure goes up, in order to keep this side equal to the same as this side, what has to happen? Volume must go down. Y'all write these formulas down. Like, I know writing a few formulas and a little arrow sound crazy, but it works, it helps. Okay, a sample of gas in a 1 liter container at 1 atm pressure is placed into a larger container. What happens to the pressure? You don't have to do the math. This is just logically thinking about it. Okay, 10 seconds. Okay, talk. Click in again. I'll give y'all 30 seconds. We're going to do one more after this. Okay, 5 seconds. Make sure you click in again. Don't forget to click in again. Don't lose points. Click in again. I think we have 48. Come on. So what did you say? Here we go. Good. So PV is equal to nRT. So what happened? We have a sample in a 1 liter container at 1 ATM. So what happens? We place it into a larger container. The volume goes up. What happens to the pressure? Pressure goes down. Okay. So that was pressure goes down. Okay. How do we have, did I unclick? That's what I did. I unclicked it. Okay. All right. Do we have time for one more? Yeah, we have time for one more. All right, one more. Sample of 1 liter, sample of gas is 1 liter at 25 degrees Celsius. We heat it to 50. What happens to the volume? As soon as we get 48 people clicked in, I'll let y'all chat. Come on. It's 48 or 1 minute, either one. I must have knocked y'all. All right, so talk, decide. Remember, PV is equal to nRT. Click in again. 30 seconds, click in again. So you should have. Click in again. Come on. Waiting. I got 40, I'm cutting it off. All right. So what happened? If our temperature goes up, what happens to our volume? Goes up. So it can't decrease, it can't be unchanged, and not enough information is given as B. Oh. All right. Try to get those clicker points up. All right, anybody on Zoom have questions? Good luck studying for your exam. Study, study. Yes, ma'am.
Is there any way I can look to see what my clicker average is?